Question number 2. This will be published on 6th of Jan. Right. So the graph shows how current I varies with the potential difference V for a resistor and a non-ohmic conductor. Okay. So I versus V graph is drawn for two different components. One is for a resistor and the other one is for a non-ohmic conductor. What do you mean a non-ohmic component? Which means it does not obey Ohm's law. Okay. So therefore you see, so it does not obey Ohm's law. It is not linear over here. Right. Now let us understand, show how that they state how the resistance of T varies with the current going through T. When the current passes through T and the current increases, then what will happen to the resistance across T? Now, so what is resistance? So first, before going to resistance, first let us understand what is the slope in a graph given. Okay, whenever there is a graph given, so first understand what is the slope. This will be your slope. So what is the slope here? This will be delta I. This will be delta V. So therefore, slope will be given by delta I divided by delta V, right? Now what do we need for resistance? Resistance is nothing but delta V divided by delta I, which is Ohm's law, right? Which should be equal to 1 by slope. Now what's happening in this case? See, in case of R, you have a constant slope. In case of T, initially slope is small, then slope starts increasing, then slowly slope keeps on increasing, which means what? As the slope increases, when does the slope increase? When the current is increasing. Okay, let me write down. When the current is increasing, slope is increasing. So as a result of it, when slope increases, which means what? Denominator increases. When denominator increases, what happens to resistance? Resistance will decrease. So what should you write here? So you should write that as I increases, slope increases. This implies RT decreases, right? Then deduce without a numerical calculation whether R or T has greater resistance at I equal to 0.4 amperes. You need not calculate anything. You just need to look into the graph and understand whether which one has a larger resistance, right? So at what current? 0.5 amperes. 0.5 amperes. Let us take 0.4 amperes. 0.4 amperes, this line, if I draw a line here, it will intersect at this point and it will also intersect at this point. Now, if I drop a perpendicular here to this line, to the voltage line, you see, it will intersect here. What is this here? This is your VR. And what is VT? VT would be somewhere over here. VT would be somewhere over here. Now, what do we understand from here? We understand that VR is greater than VT. We need not write anything over here. Now, let us go back to our question. So, now, if VR is greater than VT, then for a constant current, what is R? R is equal to V divided by I. So, this implies RR, which should be equal to VR by I, and RT, which should be equal to VT by I. I is not changing, right? So, therefore, since VR is greater than VT, what can you conclude here? You can just say RR is greater than RT, right? So, this is what you can conclude here. Okay. So, it is for 2 marks. So, you should write this and then you should conclude this one with the help of these equations. Only then you will get 2 marks over here. Okay. Next. Components R and T are placed in the circuit. Both meters are ideal. Both meters are ideal, which means what? No current is taken from here, and the infinite resistance is seen here at voltmeter. Then slide Z of the potentiometer is moved from Y to X. Slide Z is moved from Y to X. See, if suppose the slide is Z is at this point, what does it tell you? The current has a larger resistance over here. It has to cross this resistance. If it is midway here, what will happen? So if this resistance from X to Y is R, midway it should be R by 2. If it is here, what will happen? The resistance has still decreased. If I keep it here, then what will happen? The resistance is completely 0 in this region. So what will happen to the current? More current will pass in the 0 resistance regions and no current will pass in the ammeter resistance region, right? Because this is ideal, so it does not have any resistance. All the current will only pass through this one. Okay, so not through this one. This will be connected here like this. So as a result of it, every current will pass here and no current will pass over here. So that's what will happen over here. You can just write the current here. What happens to the magnitude of the current? Magnitude of the current will be equal to 0. This will be happening over here. Then estimate with an explanation. State. So you need not explain anything. Estimate with an explanation the voltmeter reading when the ammeter reads 0.2 ampere. What happens to the voltmeter when the ammeter reads 0.2 ampere? Okay, so this will take some time. So 0.2 ampere, 0.2 ampere is here. Okay, now many of the students, what they do is they have a misconception saying that they will draw a line here. Okay, and what they do is they find out what is the voltage here, what is the voltage here. This voltage is 2.8 volt, and this voltage is something like 3.8 volt. Then they will take the average of these two and write the one. That is completely incorrect. Okay, don't do this. Okay, let us read the question properly, understand what's happening. Okay, now when you say that the current is equal to, when the current in the ammeter is 0.2 ampere, where is it here? This value is 0.2 ampere, 0.2 ampere. So now this current, when it comes here, there is no current passing through this one. So this will be 0. When it comes here, this will be your current IR and this will be your current IT over here. So accordingly, it says that the question says IR plus IT is equal to 0.2 ampere. First thing. And secondly, when you have a circuit like this, you already know that VR should be equal to VT. Why? Because they are in parallel to each other. So this condition should be met, and at the same time this condition should be met. Okay. Now if I go back to the graph here, what's happening to VR and VT? What did we see there? We saw that VR should be equal to VT, right? We saw that VR should be equal to VT. But if I do it like this, you see what is VR here? VR here was seen to be 2.8. And what is VT here? Sorry, this, what is this? This is VR. Yeah, VR. And this is VT. VT is somewhere seen to be around 3.8. Do you think this answer is correct? No, this is not correct. Okay. So look for those values where VR is equal to VT. When will we have VR equal to VT? Let us say, for example, I draw a line like this. I draw a line like this. See here, this intersect VR. VR will, the resistance of, voltage at R is also 1 volt. Voltage at T is also 1 volt. Okay, but the currents are different. Okay, the current here. Now, what is the current here? The current here is somewhere around 0.2 ampere, 0.02 amperes, 0.02 ampere. And what is the current here? The current here is around 0.08 ampere, 0.08 ampere. So therefore, I will now write IR equal to 0.08 ampere, IT is equal to 0.02 ampere, I is equal to IR plus IT which will be equal to 0.1 ampere. And when will this happen? All this happens when VR is equal to VT is equal to 1 volt. Okay, at 1 volt is what is happening. But what do I need here? I need this value to be 0.1 ampere. Look at this. Look at this here, the condition. The condition says IR plus IT should be equal to 0.2 and VR should be equal to VT. See, this VR equal to VT condition is seen here. VR is equal to VT is seen over here. Okay, but unfortunately, IR plus IT is equal to 0.1. It's not 0.2. So therefore, this will be incorrect solution. Now what we do is we need to test for each and every value. It can happen anywhere, right? Then you might be asking, hey, how do I know? Where should I test this? Let us start doing it one by one. Okay, then you will get probably a proper answer. Let us test here. At VR is equal to VT is equal to 2 volt. Okay, VR equal to VT is equal to 2 volt. Let me write it down separately here. Let me take up my space here, and then I'll write it down here. So I'll now write VR equal to VT equal to 2 volt, and then for this let me find out what are your values of IR. What is IR here? So what should I do? I should draw a line correspondingly at VR equal to VT equal to 2 volt and see where does it intersect. It intersects at this point. What is this point over here? 0.06 over here, right? So IR, so what is this value? So it intersects this curve. Which is this curve? This curve is T curve, non-linear one, right? 0.06 over here, 0.0606 ampere. And what is IT? See, this goes like this, it hits here. So this value is 0.1, 0.12, 0.14. So this should be 0.14 ampere. Now if I take the sum of these two, what do I get? I get 0.2 amperes. Okay, this is what is required, right? So go back to this. VR equal to VT equal to 2 volt. Total current to the ammeter is 0.2 amperes. See? So VR equal to VT is equal to 2 volt. At 2 volt, IR plus IT equal to 0.2 amperes. Why IR plus IT, if you ask me? That is nothing but the total current which has been observed in the ampere. Okay. So therefore, because the question also says at 0.2 amperes in the ammeter reading. So therefore, we see that IR plus IT is equal to 0.14 plus 0.06, which is equal to 0.2 amperes is possible only at VR equal to VT equal to 2 volt. Now you can ask me, so is this true only for 2 volt? Is it possible for any other volt? You can check it over, but anyway, this is an examination. So in an exam paper, we ask only for one answer. If you are very much curious, you can look, okay, where do we have such kinds of functions, where is it possible, and so on. Only for 2 marks. Let us restrict ourselves for 2 marks. Okay, so let us not do a big research or do a PhD on this. Right. So with this, I think we have come to an end to this question. This question is really interesting. Learn this. Okay, lot of concepts will come to your hand by doing this one. Thank you.